What you're going to see today is probability and two ideas, union and intersection. And this kind of goes with the other thing we were making where we were talking about sample spaces. We were talking about a probability tree. I want to state what the difference is between a union and an intersection. So you may have heard the word union in a prior time. Union meaning two things come together. More than two things. You may think back to history class to form a more perfect union. So it's when you're putting two things together. So in this example, the table to the left shows all the possible sums when rolling two four-sided dice. And you see that I have two conditions, rolling a 5 or rolling doubles. So if I say union, what I mean is I'm adding together the probability of the 5 and adding together the probability of doubles. What you're going to see for the new word is mutually exclusive. The example with mutually exclusive is that none of my conditions are on top of each other. So if I look at the yellow here, the yellow represents doubles. Double 1, double 2, double 3, double 4. And the ones highlighted in blue represent combinations that add to 5. A 1 and a 4 add to 5. A 2 and a 3 add to 5. But you can see that they never actually hit each other. All four of these responses are unique from these four. So we call that mutually exclusive. The answer is the union of those two probabilities. So the probability for a 5 was 4 out of 16. The probability for doubles was also 4 out of 16. And then I end up with a total of 8 out of 16, which is 1/2. And that worked great for us, because none of these repeated themselves. They were all unique, they were all different, so we counted all 8 of them in order to get our probability. The problem with intersection is if I look at this picture, this response right here is really blue and it's yellow. So how do I deal with that? If I did just like I did when we were doing mutually exclusive, and I say, well, I could find the probability of getting a 6, and then I could find the probability of getting doubles, that would seem like a good way to do it. Getting a 6 is 3 out of 16, because there's 3 ways to get a 6. Rolling doubles, there's 4 ways to get doubles. So 3 plus 4 equals 7. 7 out of 16. But if we look at the picture, we can clearly see that there's only 6 favorable outcomes here. I've got the 5 that are in here plus this 1. So how is it that I got 7 out of 16 when I try to do it with the math, but I get 6 out of 16 when I look at my sample space and count it out? Well, our answer is probably easier to see if I just make a table. If I make a table, I counted that 6 when I did my rolling a sum of 6, a 3 and a 3, but I counted that same exact outcome, a 3 and a 3, when I counted rolling doubles. So essentially what I did is I counted that same outcome twice. So if we go back and we say, well, I was supposed to get 6 out of 16, but I got 7 out of 16, it's because we counted this same outcome twice. That's why I got a wrong answer. When I look at my table, I can clearly see, oh, I double counted 3, 3. So we've got to look at the intersection and say intersection are the number of things in the list which were identical, the place where the two of them come together. So in this particular symbol, you'll see here, I'm writing the probability of 6 intersecting with doubles is 1 out of 16. I had one outcome that was double counted. So all I have to do in the math formula now is to take that intersection and subtract it out of the answer that I got when I added the two together. So the probability I got a 6 was 3 out of 16. The probability that I got doubles was 4 out of 16, but one of those was double counted. So I have to subtract that one out in order to get my answer of 6 out of 16. So if I just summarize, mutually exclusive means that each outcome meets only one condition in the probability statement. It's not going to meet both of them. So if I look at my example, rolling a 1 or a 6 with a 6-sided die, I can't roll both numbers in the same roll. So I don't have to worry about an intersection there. I'm either going to get a 1 or a 6 or none of those. I can't get them both at the same time. Getting all heads or all tails when flipping 3 coins. If I got 3 heads, then I couldn't have gotten 3 tails, so I don't have to worry about an intersection there. I'm either going to get the head or not. And then cutting a face card or a 5 in cribbage, a face card cannot also be a 5. If it's only one card I'm cutting, there's no way for those two things to be happening with the same outcome. When I go over and write my formula, the very scientific official way to write it is like this. The probability of A or B is the probability of A plus the probability of B. And we call that a union because we're just combining those two values together. If I were looking at an intersection, then one of my outcomes meets more than one condition at the same time. So an example of that would be rolling a sum of 8 with 2 6-sided dice or rolling doubles. Because if you rolled a pair of 4s, you'd be meeting both conditions with the same roll. 4 plus 4 is 8, so it gets counted when you're doing the sum of 8. But 4 and 4 is also a double, so it would get counted when you did the probability of rolling a double. So it met both conditions that you were checking for. That makes it an intersection. If we go into the real world application, an employee has 10 plus years of experience or is bilingual. Well, the same employee could have both of those characteristics. So if you were making a list of all the employees that had 10-year plus, and then you had a list of how many employees were bilingual, you might be double counting some of the employees. Maybe one of those bilingual employees has also been working in your business for a long time. And then if I were cutting a 10 card or a heart in a game of cribbage, notice 10, jack, queen, king all have a value of 10, but they're also hearts. So there my intersection would have 4 elements in it, one for each of those cards. So we just want to keep track of when I have an intersection in an OR statement, we have to remember to subtract that out after. So the formula is going to show the probability of A or B when there's an intersection is the probability of A plus the probability of B. That was the union. But then I have to subtract out the intersection. I have to subtract out those things that I double counted. So the final thought that I wanted to put on to this kind of unit as we're starting to progress a little deeper is not every problem I give you is going to have an OR condition. A lot of times we're looking for just one specific outcome. And sometimes that outcome involves a more complicated sample space. So we've been rolling 2 dice and looking at their sums. But what if I wanted to know the probability of 3 people flipping coins simultaneously and getting all tails? Well, now my table may not be as nice to use as it was in the previous problem. So this is what my sample space could look like. It could just be a listing. So here I have H stands for heads. I've got 3 people flipping. That's why I have 3 things listed. So let's say the first person flips a head. Head, second person flips a head, third person flips a head. First person flips a head, second person flips a head, third person flips a tail. First person flips a head, second person flips a tail, third person flips a head. This is how I'm writing out all of my possibilities. And just out of convenience, I split this list so that it wasn't as hard for me to look at. I just made 2 lists, one assuming that the first person had a head, and then one assuming that first person had a tail, and it just helped me organize my list a little easier because now I just have to jumble the numbers in the back. Notice the pattern in the back. Once I've set these to all be H, HH, HT, TH, TT. I just made simple switches to get down all of my combinations. Same thing with the tail. What if I replace that last tail with a head? What if I switch those two? What if the last 2 are both heads? So that's how I made my sample space. Now, those of you that have seen probability trees before, in a previous class I talked about how probability trees are sometimes helpful. this is a good example of when a probability tree might be helpful. So that first person got a head or a tail, the second person got a head or a tail, the third person got a head or a tail, and I can see when I look at this that there's 8 outcomes that are possible. Now, if I were to put some probabilities on it, the reason we like probability trees so much is when I get down to where I need, I just have to multiply all the probabilities together to get my answer. So if I say, what's the probability that all 3 players flipped a tail? Well, the first person had a 50-50 chance. We call 1/2 50%. So we had a 50% chance of getting a tail. And then player 2 had a 50% chance of getting a tail. And then player 3 had a 50% chance of getting a tail. So if I wanted tail, 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 I would have to do 1/2 times 1/2 times 1/2, which is 1/8. So the way I get a probability answer out of a tree is I just multiply down. And here, all of my outcomes are equally likely, so it's half everywhere. All of them are half times half times half. The only part where you're going to run into a little bit of a struggle here is if I give you a condition that has more than one favorable outcome. So let's say I say the probability that you get 2 heads. Well, now there's multiple paths that will get me to 2 heads. If the first person had a tail, but then the second person and the third person had a head, then I would end up down here in my diagram. See how that's a tail, a head, and a head? There's 2 heads there. So that's one of the ones that I had to count. And here it is, tail, head, head. Now, if the first person got a head and the second person got a head, I'm looking for only 2 heads. So the last person would have to get a tail in order for me to have 2 heads in that chain. So I'd have a half to get here, times a half to get here, times a half to get here. That would be 1/8. So I had an 1/8 from this one, tail, head, head. That was an 1/8. Head, head, tail. That was an 1/8. And then I could have had a head with the first person, a tail with the second person, and a head with the third person. That's head, tail, head. That's 2 heads. So that's the last one I had here, and that's why I have another 1/8. So each of those probabilities were 1 out of 8. There were 3 ways to get them. So I ended up with 1/8 plus 1/8 plus 1/8, which is 3/8. So we now see how the probability tree works, how it could be helpful. If we were looking at any real problem here, I could ask any question. I could say, what's the chance that you get 1 head? And then you could say, well, if you're looking for 1 head, then second and third person had to get tails. If I were saying, what if everybody got a head, all 3 of you? Well, now we're talking about just this part of the chain. So that's how you're going to do all these probabilities. And you'll see they're all variations of this. They're not all equally likely. As you saw, if I go back, 3 tails is only 1 out of 8. Here, when I got just 1 tail, 2 heads means 1 tail, it's 3 out of 8. So they're not equally likely as you get down here, because sometimes it's easier to get 2 heads than it would be to get 3 heads. Or it's easier to get 2 tails than it would be to get 3 tails. So that's probability for you. Enjoy your work this week.